Linear Algebra, a lecture on linear independence. In this lecture we're going to get more into the maths of linear independence and linear dependence. So, let V be a real or complex vector space. A finite subset V1 to Vk in V is defined to be linearly dependent if there are scalars A1 to AK not all zero, such that A1, V1, remember V1's a vector so it's underlined, plus A2, V2, up to AK, Vk is equal to 0. Now what does this mean? Intuitively, all we are saying is that linear dependence means you can go nowhere, i.e. go to 0, and finish at the origin also. Not only though by taking 0 of each instruction, so taking 0 of one step forward, 0 of one step sideways, but also by taking some non-zero combination of the vectors. This is what this bit means. We are taking some non-zero combination of vectors and still getting 0. So we're taking 3 of V1 plus minus 2 of V2, and we're ending up at 0 still. Conversely, a set of linear independent vectors is simply the opposite of linear dependence. It says that for the set V1 up to Vk is 0 only when the scalars A1 to AK are all 0. So in equation form, A1 So this is only true when all the scalars A1 to AK are all 0. What does this mean again intuitively? That there's no way that these vectors in some sense cancel out. You can't have 5 of V1 and minus 2 of V2 and a bit of Vk all adding up to get 0. You can only get 0 if you have 0 of V1, 0 of V2, 0 of Vk.